Alright, so what we're going to do in this video is look at some slightly more complicated type of momentum impulse theorem problems. Not complicated is a relative term, but it's, just looking at this a little bit differently. So here's the equation for just regular momentum. Kilogram meters per second kilogram meters per second. So we've got mass times velocity gives a vector quantity called the momentum. Okay. We also know that the momentum impulse theorem says that the impulse is really just the average net force acting on an object multiplied by the time that average force is acting on the object, and it just equals the change in momentum. So impulse is nothing more than the change in momentum. This here has units of Newton seconds. This has units of kilogram meters per second, which makes them equivalent. So in this question, what we're going to look at, it says here, a net force, this goes back to like grade 11, seriously. A net force of 8 newtons acts on a 5 kilogram mass for 8 seconds. If the final velocity of the mass is 40 meters per second, then it's going to ask us some questions. Okay, it's going to say what is the impulse in the mass, what is the initial momentum of the mass, and what is the initial velocity of the mass. Well, in this type of problem, I mean, we really could just figure out the acceleration. Again, this is easy. 8 divided by 5 would tell us the acceleration. If you multiply the acceleration, which if we do 8 divided by 5 and then multiply it by the time, which is 8, we get, we would basically be able to figure out the change in the speed. And if we know the final speed's 40 and we know what the change in the speed is, then we can figure out what the initial speed of the object was. So it's very straightforward to use regular dynamics and kinematics to solve this. But we're going to look at it a little bit differently. So finding the impulse. Well, as we know, the impulse is simply the average net force acting on the object multiplied by some time, and that equals the change in momentum. Again, I'm saying it over and over, but I'm just trying to hash out that this is as simple as it is. We know that net force is 8 newtons. We know the time it acts is 8 seconds. So we end up with a momentum change of 64 newton seconds, or an impulse of 64 newton seconds, or a delta P of 64 newton seconds. Now, if we were to graph this, here we have the average net force as a function of time right there. So this says, how is the net force changing as a function of time? And over here we have time. Well, in this case, the net force was 8 newtons. And throughout time, in this case here, the net force remains constant for 8 seconds. Okay, so the net force remains constant for those 8 seconds and just potentially continues on from there. What is the initial momentum of this mass? Well, the initial momentum of the mass, since we know that the impulse is the change in momentum, and we know that change in momentum is mv2 minus mv1, we can actually solve, which really is our, this is the initial momentum right here, which is p1. So, we could even look at this part here and say this is really just p1 vector, and the other one is p2 vector. So if I rearrange this formula, what I would find is that mv1 vector equals mv2 vector minus the impulse, or minus delta p. It doesn't matter, it's the same difference, right? So what we can do is we know that this term here just represents the momentum. Well, the mass was 5, v2 was 40, the impulse or the change in momentum was 64. So the initial momentum is going to be therefore 136 kilogram meters per second, or 136 newton seconds. But since we're talking about momentum in this case, we're going to call it kilogram meters per second, which is just a nicer way of talking about it. Now it says, what is the initial velocity of this mass? Well, since we know that P1 is mv1, we can solve for V1 by just saying it's the momentum divided by the mass, 136 kilogram meters per second, divided by 5 kilograms. So our units cancel out, and we end up, or divide out, sorry, and we end up with meters per second. So V1 was 27.2 meters per second. Okay. One other thing I want to point out is that, so there you can see the solution there. So the object changed its momentum by 64 Newton seconds, which means it was gaining momentum. So that means that it started out with a momentum of 136, gained 64 to get to the final momentum. So if we add 64 to 136, we would actually find out that that is going to give us 180. Well, what is 5 times, so the final momentum is m times v. 136 and 64 is 200. And if we take 5 times 40, we get 200. So we can see that the final momentum is 200 Newton seconds, or kilogram meters per second. And it matches perfectly. Another thing I want to point out, on an average force, an average net force as a function of time, so this is the net force as a function of time, you'll see that this is 8 newtons over 8 seconds. Well, we find out that if we take the area is length times width, it's 8 newtons times 8 seconds is 64 Newton seconds, which is exactly the impulse. So what we see here is that the impulse equals the area bounded by the x-axis and the y-axis, so this area here. That's what the impulse is. In this case, it's positive. So this is what's known as integral calculus. Integral calculus is the sort of the opposite, if you will, of differential calculus. So in calculus in high school, what you're learning is the derivative, finding the slope of a tangent. Turns out that if you do the antiderivative, meaning working backwards, and then evaluate that over a certain limit, over a certain time period, then what you'll find out is that you'll actually end up with the area. And the area is called an integral. So if we do the integral, we'll find the area, and that area, in this case, represents the impulse. We'll do more about that later when we talk about a time-varying force. So if we flip this over, what we're going to look at here is that I wrote here, area equals impulse equals change in momentum. Now, it says here, very important. I mean, star this, highlight it, whatever you need to do. The area between the x-axis and the line or curve represents the impulse, or the change in momentum of the object. For simple net force functions, you can calculate the area easily. For more complicated time-variant forces, integral calculus must be used. So we have to be aware that, in some cases it's easy just to use simple math, just finding an area, length times width, and all that kind of stuff. But other times you're actually going to need to use calculus. And we'll learn more about that as we progress. So, for example, if I had a time-variant force, an average net force as a function of time, and it was to look like, let's say this, and here's some time, and here's the net force as it changes with time. It's in the positive, negative. It could be positive or negative. So let's say that it looks like this, and then dips down, comes across, goes up, and across like this. So this force is changing. So it starts out at some positive value, then it decreases with time, and then the force is pushing in the opposite direction. Then it levels out and stays at a constant force in that negative direction for a little bit. Then it starts to decrease in the negative and becomes 0. So that's 0. So now there's no net force. And then the net force continues to increase till it remains constant at some point here. This would be really hard. If you wanted to do Newton's second law, so if this started out at some speed and you want to figure out, oh, how fast is it going after this force acts on it, after this time variant net force acts on it, you would need to find the acceleration in each stage and then calculate it. And the worst part is that here, where there's a slope, that means the force is changing every little bit of time. So you would have to do Newton's second law for each individual single point infinitesimally, like every single point, and then add them all up to figure out what that what the change in speed or the change in momentum would be in each of those cases. And that's extremely difficult and time consuming. And that's what calculus is for. Integral calculus says that you can apply the principles of integral calculus, the fundamental theorem of calculus, and then you're actually able to evaluate this area, and that the area that you get from this tells you exactly what the value of the impulse or the change in momentum would be for that time variant force. It's amazing. Again, this would give you a positive value, this would give you a negative value, and this would give you a positive value. Okay, so the net overall impulse change would be positive in this case. And you could actually just make little triangles, make little rectangles, and find the areas and all that kind of stuff to figure out what that delta P is. So just calculate the area. Now, and add them up. And the word integral calculus just means add them up or sum them up. In actual fact, that sigma, the sigma sign that we used before, that's just the average. That's like the delta of average velocities and average changes, and therefore the sigma is just the integral version of what's called an integral sign. So it's the discrete version of that. So in the real world, what we actually have is this. Functions are even more dynamic. They don't actually change as abruptly as other forces might do. So you can't always just easily add up the areas that you see here. So what you might get in real life is a force varies maybe like this, right? And in that case, finding this area right here and adding it up and finding that area is actually a lot more complicated. So in this case, what we're going to use is something called integral calculus, and it will solve it for us. Well, not for us, but it gives us a mathematical tool to be able to evaluate the area under that smooth curve of a time variant force that's not behaving the way we'd like it to. All right, we'll do an example where we're not using integral calculus. This is an extension that we're going to work on. We're going to focus more on the types where you can actually just find areas of rectangles and triangles. Very simple. So in this case here, we have an object of mass 3 kilograms, and it has an initial velocity of 7 meters per second. There's a force that acts on it, but that force changes with time. And rather than finding out the accelerations in each interval and then trying to add them all up and find the final speed, we're going to invoke this momentum impulse theorem. So what we start with is we know that V1 is 7 meters per second. We know the mass is 3 kilograms. And we know that we're trying to solve for the final speed. We know that what we're doing is the average net force acting over time is the change in momentum. So we know the equation that we're going to invoke here. And we know that this just equals the area under the curve. Now, pay careful attention to what we're going to do here. The first thing we're going to do is break this into pieces. Okay, like this. And I've got section 1, section 2, 3, 4, and 5, like so. So we're going to look at the change momentum for each section that's right there, and then find out the total change in momentum. So let's find the area. So for area 1, each unit here is 1, 2, 3 seconds, and then up is 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons. So here we have the first bit for number 1 is we've got 2 times 3, so it's 6 Newton seconds. Okay, we're going to follow the same thing for section 2. It's a triangle, so we have the height of it is 2, the base of it is 2, and we divide it by 2, and we get 2 Newton seconds. Notice the units work, newtons times seconds, that's the area. So it's areas of impulse. 3, we've got negative, because now we're in this is the positive section, this is the negative section. So we've got negative 1 times 1 divided by 2, area of a triangle, gives us negative 0.5 Newton seconds. And then we go to number 4. 4 is 1, sorry, the base of this was 2. So it's negative 1, the base was actually 2, divided by 2, so it's negative 1 Newton seconds. Negative 1 Newton seconds. For number 4, we've got 1 by 1 divided by 2, which is 1 Newton second. Sorry, 0.5 Newton seconds. Messing this whole thing up. 5 is 1 Newton by 2 seconds. We don't have to divide it by 2, so we get 2 Newton seconds. So the total area is 6 plus 2 is 8. 8 minus 1 is 7. 7 plus 2 is 9. 9 plus 0.5 is 9.5 Newton seconds. So the total impulse, or the change in momentum, is simply 9.5 Newton seconds. So what we do now is we come over here, and we know that now delta P, the change in momentum, was simply 9.5 Newton seconds, or kilogram meters per second. And we know that delta P is simply P2 minus P1. So if we're trying to solve, we can rearrange for P1, and that's simply P2, well, we have delta P vector minus P2 vector, like so. And if we then just change the signs of these, oh, we're trying to calculate the final velocity. So we're trying to find P2. So again, me messing up. Seems to be midday for that right now. There we go. So I just was solving for the wrong one. So P2 is simply delta P plus P1. Okay. So we know that this is mv2 is delta P. I'm just going to drop the vector signs for now. Plus mv1. Like so. So the change in momentum from our area was 9.5 Newton seconds, plus the mass was 3, the initial speed was 7, divided by 3. V2 is approximately 10.2 meters per second. 21 plus 9 is approximately 30, divided by 3 is approximately 10 meters per second. So that's the final speed. So if it undergoes, if this time variant force acts on it for this time that you see here for the 10 seconds, 3, 4, 5, 6, 7, 8, 9, 10, for the 10 seconds it's acting on it, then you would see that you would get a change. The speed would go from 7 meters per second to 10.2. We could also figure out something else. We could figure out the average net force. Well, average net force times time is equal to the change in momentum, or the impulse. So if we wanted to figure out what sigma FAV is, you just take the change in momentum divided by the time. So that's 9.5 Newton seconds divided by 10 seconds, because that was the total time, 0.95 newtons. So now what's interesting is that this is your average net force. Well, sigma F equals ma, right? And if we know that the mass is 3, and we know that the net force is 0.95, the average net force is 0.95, and we divide it by the mass, we could actually determine the acceleration. So we could actually take the 0.95 divided by 3, and we could get the acceleration. If we knew the acceleration, we multiply it by the time, which is 10 seconds, and then we add the 7 meters per second, and you would get exactly 10.2 meters per second. And just to prove that, you can do try to pull up the calculator that you can check that calculation. Another way of thinking about this is that with this average force of 0.95, it means that if I were to find the mark right here of 0.95 and draw a straight line across, that would be like saying if I applied an average net force of 0.95, right like that, okay, and I did that for 10 seconds, 10 times 0.95 is 9.5 Newton seconds. So the area of when I have the average net force of that, that is equivalent to all these other areas. So that area that I just did there, the green one, is equivalent to this, plus this, minus that, plus this, plus that. It equals exactly the same thing. And so whether you're using the average net force or looking at it, the change in momentum as it moves through with this time variant force, you can do those calculations. So what you're going to do now is you are going to work on the problem set, momentum impulse theorem questions. There are 8 of them in total, and then an additional practice one at the back. So we're going to do that over the next 2 days to complete this work before we move on to actually looking at how objects collide and what momentum does in that case.